All right, so when we're referring to a particular substance, there's actually going to be several different ways that we can um, represent that substance. And the simplest and probably the most common one is just going to be the molecular formula. So we can see for something like methane, where it's got one carbon, four hydrogens, the molecular formula is just going to be listing essentially what atoms or what elements do we have, and then how many atoms of each of those elements do we have. So this is something that you're probably already somewhat familiar with. Um, but with it, just recognize the molecular formula shows us exactly how many of those atoms we have. We're going to see a little later on, there's going to be something similar to the molecular formula, where it's just going to be the lowest ratio, though. So in this case, this is showing us exactly what we have. We've got one carbon and four hydrogens in a molecule of methane. Um, and then in addition to that, we can use what's known as a Lewis structure to show the structural formula. So in this case, we're showing what atoms are bonded to what. We'll ultimately learn if we had CH4, this is the only way we could have that arranged. But we'll see later on, we can have different structures with the same molecular formula. So the structural formula, like I said, shows us what atoms are bonded to what. And then with that information, we'll do this in the second quarter of the Gen Chem series. But we'll be able to use the information about that structure, or we'll be able to use that structure itself, I should say, to determine specific information about that molecule. And then when we do kind of get to that point where we're drawing these structural formulas, we'll also see that there's something a little bit more related to kind of these two. We won't do it in terms of the ball and stick, but it'll actually kind of be a combination of B and C. And that'll give us the best idea of what that molecule actually looks like in three-dimensional space. We'll use the model kits in lab sometimes, so we'll actually see stuff like this. But when we look at the structural formula, all that's simply doing is showing what atoms are bonded to what, but it doesn't actually reflect the true three-dimensional shape, because if we look at the structural formula for methane, kind of just looks like a T or a plus sign. But what we're actually going to have with the three-dimensional shape is three of those hydrogens. So we'll have the central carbon, but then we'll have three of the hydrogens kind of making a triangle at the bottom. So it's a little hard to tell with the image here, but these two carbons on the left and the right are actually pointed backwards, and they would be on the same plane as this one at the front. But then we have the fourth one just pointing at the top here. So we would actually wind up with a tetrahedral shape. And that would give us the best understanding of how that molecule is going to behave. What are the chemical properties going to be like, at least in terms of reactivity and a few other things. And even some of the physical properties, such as like boiling point, melting point, things of that nature. And then if we look at benzene here, we can see the same thing. So in this case, the structural formula actually does a decent job of showing what this molecule would look like. But even with these, and even with the ball and stick model here, we're going to see that the representations are actually a little bit misleading. But we'll cover that exactly in the second quarter. But again, we're just showing what atoms are bonded to what. In this case, we can see we've got single and double bonds. So we'll go over those in the second quarter as well. But we're just showing we've got 6 carbons in a ring here, with one hydrogen sort of poking off of each of those carbons. And that's why the molecular formula would just be C6H6. We've got 6 carbons, we've got 6 hydrogens, excuse me. And that's why if we were ever working in the lab, we would never just have a bottle like this, actually. We would always have either with a piece of tape or whatever, or the chemical bottle itself. So if we got it from the manufacturer, there'd be a label on it, because we always want to make sure that when we're working in the lab, we know exactly what everything is. So we can't just visually assess this, look at this bottle, and know for certain it's benzene. So that's why we want to label those different containers. And then with the molecular formula, like I said, showing exactly what we have in that substance, it's going to be important that we use the correct notation. So when we're thinking about the chemical symbols, we capitalize that first letter always. If there's a second letter, like with magnesium or sodium, copper, whatever it may be, we lowercase that one. And then when we've got multiple of them, that we use the subscript to indicate that. Because if we have HNO or HNO2, HNO3, all of those would be the same collection of elements. but because we would have a different number of oxygen in each of those are representing entirely different substances. And then like with, carbon dioxide's on here twice, but like we saw with carbon monoxide versus cobalt, just a lowercase o represents something entirely different. So we just want to make sure we're using the proper notation for those different molecular formulas. And with this, just remember, elements can also be considered molecules. So in some instances, we'll have just a single atom or individual atoms of that substance. So something like helium, a lot of the metals. So we could just write He for helium, Fe for iron, Na for sodium, whatever it may be. But with certain elements, we're going to have them exist in the diatomic state. So diatomic, the thing about di, just like in carbon dioxide, there's two oxygens. Diatomic is just referring to two atoms. So that's what we see here with hydrogen, with nitrogen, with oxygen, everything in group 17. So that the halogens, so fluorine, chlorine, bromine, iodine, all of those elements are going to be diatomic in their elemental state. And then somewhat similarly with phosphorus and sulfur, these wouldn't be diatomic because we've got 4 phosphorus or 8 sulfur in those elemental molecules, but we still have a collection of those atoms. So we want to make sure that we're using this correct notation, because if we just say hydrogen with just a single H there without the letter, or without the number, excuse me, that's representing something entirely different. So you can see up here, sulfur, we've got the structural formula, just showing that we're going to have 8 sulfurs in a ring. You can see a little bit more of the true shape of that molecule. So it's not just going to be kind of a flat octagon. We're going to have some bends in there. It's going to be going backwards in some cases. Like you can see these two atoms, the bond between them. And then, like I was saying, with hydrogen, we don't want to just say H if we're talking about elemental hydrogen. That'll be H2, where we have the molecule. This would just be one single atom of hydrogen, which would be pretty relatively uncommon, or extremely uncommon, really. But those are going to represent two different substances. Same thing if we put 2H rather than H2. Now that's saying we've got two individual hydrogen atoms, whereas H2 is saying we still have two hydrogen atoms, but this time they're bonded together to make that molecule. So it may seem like a just sort of a small, unimportant difference, but by not using the proper notation, we're not actually referring to the substance that we may think we are. And then, like I said, with the molecular formula, this is showing exactly what we have in that molecule. So with N2O4, we've got 2 nitrogen in the middle here, and then the 4 oxygens just coming off of those. Benzene, we already saw 6 carbons in a ring, see the hydrogens on the outside. C2H6O2, so this would be a ethyl diol, because we've got 2 alcohol groups on the sides there. But with the molecular formula, like I said, that shows us exactly what we have. We also have what's known as the empirical, which just shows us the simplest ratio. So if we look at the molecular to the empirical for these ones, we can identify how we can determine those. And like I said, it's just the simplest ratio. So we're just going to find a common factor between these subscripts. So with N2O4, we really have 1 nitrogen for every 2 oxygen. And that's why the empirical formula is just NO2. Similarly, for the other ones, we've got 6 and 6. So the greatest common factor there would just be 6. So the empirical formula, the simplest ratio of those elements to one another in benzene would just be CH, because for every 1 carbon, we're going to have a single hydrogen. And then for C2H6O2, again, we're trying to find the largest common factor between all of these different elements. And in this case, it's going to be 2. So we'll just wind up with CH3O as the empirical formula. And in some cases, the empirical and the molecular would be exactly the same. So let's say we had C2H6O. So we just had a single oxygen there. Then the greatest common factor would just be 1. So nothing would actually change between the empirical and the molecular. But the reason we have the molecular is, one, just so we can see that the ratio in some cases. We'll see in chapter 3 there's going to be a particular type of question where if we know the empirical formula and we know how large that molecule is, we can use those 2 pieces of information to actually get the molecular formula. So if we think back to something like mass spectrometry, we could use that or some other analysis to figure out the percent composition of the different elements in a sample. And we can use that to get the empirical formula. But because we could have multiple molecular formulas with that same ratio, we need to know how big the molecule is overall, so we know exactly what it is. Because if we go back here, NO2, that could be the molecular formula. And if that was the case, the empirical would be the same. But we could have N2O4 have this empirical formula. We could have N3O6 have this empirical formula. So because there's going to be multiple samples, multiple substances that could have the same empirical formula, we can't automatically go in that reverse direction. So we can't automatically go from empirical to molecular without actually knowing the molecular mass or the molar mass of that substance. Like I said, that'll be something that we actually do in chapter 3. But looking at the examples here, see if you can just pause the video and take a moment to go through these and take the molecular formulas we have on the left and convert those into the empirical formula. And like I said earlier, in some cases, they may be exactly the same. But just go ahead and pause the video because I'm just going to click through and show the answers in 1, 2, 3. So looking at these ones, again, just find the largest common factor with those subscripts. So for P4O10, greatest common factor is just going to be 2. So we can divide each of those subscripts by 2 and get an empirical formula of P2O5. And with this, anytime the subscripts are all even, we can automatically divide by 2. There may be a larger common factor that we may be able to use, but we can always at least start by dividing by 2. But you'll always want to check to make sure that we can't then even simplify the empirical formula even further. Because let's say instead of P4O10, let's just say we had P4O12. If we divide these by 2, now we would have P2O6 in this case. But again, these are still even, so we really could have divided by 4 to begin with. And we would just have a empirical formula of PO3 in that case. So if they are even, you can at least divide by 2. There may be a larger common factor. So like I said, we could have just gone divided by 4 and gone straight here. But always check the empirical formula you get and just make sure that can't be simplified any further because you might have just missed the largest common factor. You might have just used some common factor instead of the largest. So always just double check to make sure that you can't reduce those further. And then also, anytime we've got a single atom of one of those elements in the molecular formula, we can't reduce it any further. So with H2O, we've got one single oxygen here. There's not going to be any common factor larger than 1 in that case. So if we wanted to, we could divide by 1, but we're going to wind up with that same thing. And that's why this last one also has the same empirical and molecular formula. We've got a single oxygen. There's also no common factor between 5 and 12. But even if there was, there's just a single oxygen here, so we can't reduce that any further. And then with these middle 3, N2O4, C10H22, each of those we can just divide by 2. And then again, double check C5H11, 11's odd, 5's odd, but there's going to be no common factor between those, so we certainly can't divide by 2, but there's going to be nothing that goes into both of those evenly. So that'll be the empirical formula there. And then in this case, we've got C6H18O3. So our greatest common factor is just going to be 3 there. Goes evenly into all 3 of these values. So we'll have C2H6O. And then with this next one here, pretty much the same thing. In this case, we're not given the molecular formula directly. So we want to use the information about glucose, or we want to use the information about metallaldehyde to get the molecular formula and then simplify that into the empirical formula. So with glucose, you're probably familiar with this formula, C6H12O6. So that comes up quite a bit in biology when you're looking at like photosynthesis and cellular respiration and things of that nature. But with C6H12O6, we've got a common factor of 6 in this case. So what we're really just going to wind up with is CH2O. And then with the metallaldehyde, we can do the same thing, C8H16O4. And this 4 is going to be our greatest common factor. So we're going to be able to divide 8 by 4. We're going to be able to divide 16 by 4. Of course, we'll be able to divide 4 by 4. So we'll wind up with a empirical formula of C2H4O. But again, in each case, these first ones, we're just taking that information and writing it as the molecular formula, and then identifying the largest common factor. So 6 in this case, 4 for the second one, so we can reduce those subscripts to the simplest ratio. And then with the last piece of this section of the chapter, there's going to be one more kind of section we look at with the periodic table and actually seeing how compounds come together. What are the differences between an ionic and a covalent compound? But like I mentioned earlier, with the molecular formula, that just shows us what atoms we have, what elements we have, how many of each of them do we have. But in some cases, we can take those atoms and rearrange them differently. And that's going to be known as an isomer. So you can see two examples of C2H4O2. So in each of these molecules in the middle, we've got 2 carbons, 4 hydrogens, and 2 oxygens. But if we look at them, we've got 2 entirely different structures for acetic acid. So this is just going to be the substance that gives vinegar its characteristic smell. So with acetic acid, we've got the 2 carbons in the middle, and then both of the oxygens kind of branching off that carbon on the right. In the case of methylformate, now we've got an oxygen in the middle of both of those carbons. We still have a double bonded oxygen on one of them, but we can see we don't have the same arrangement of those atoms to one another. So even though these have the same collection of atoms, because they're arranged differently, these are going to be 2 entirely different substances. And like I said, acetic acid is just the substance that gives odor its characteristic smell. Like it says acid here. It is an acid, but it's not a strong acid at all. So it's not going to be something like hydrochloric acid that could really do a lot of damage unless you had it in extremely high concentrations. And then methylformate is primarily going to be used in as a solvent. I think it's used in the manufacturing of different organic chemicals. So organic chemicals are just going to be carbon-based substances for the most part. But it's going to be very, very different from the acetic acid, even though we've got that same molecular formula. And those would be examples of structural isomers. So just taking those same atoms and just connecting them in a different order. What we're also going to see here on the next couple of slides is what's known as a spatial isomer. And these are a little bit harder to fully understand, I think. But these can have huge consequences in terms of the health of humans and other organisms as well if they were exposed to it. But in this case, instead of connecting those in a different arrangement, we're still going to have the same atoms bonded to one another. But in this case, the way that they're sort of oriented is going to be different. And we'll be able to see that on the next slide here. So you can see plus carbone, negative carbone, S and R. So those are just different designations we can use to distinguish between these 2 spatial isomers. But if you look at their structural formulas, it's essentially the exact same thing. CH3 carbon, we've got a ring of carbons, a double bonded oxygen coming off there. So they look like mirror images. But what these are going to be is non-superimposable mirror images. So if you think about your hands, for instance, as long as you have the same number of fingers on both sides, they're going to be mirror images of one another. But then if you put your palm down for one hand and then put the palm on top of that for the other, you'll have your thumb for your right hand on one side, you'll have the thumb for the left hand on the other. So they're not superimposable. And let's see the same thing with these molecules here. So in the case of carbone, I believe these are caraway seeds and then spearmint maybe. But when we look at the image at the top here, they just look like mirror images. But the way we can identify that they're not superimposable is if we take either of the isomers and just kind of position it so that they're in the same sort of general setup. So in this case, you can see the red oxygen is now pointed to the right in each case. And it's a little hard to see, but when we do this, with the hydrogens at the top, if we just kind of look at the way some of these atoms are positioned, you can see the hydrogens at the top are now facing different directions than we have here. But the big piece is going to be down at the bottom, kind of in this. If we focus on this carbon here, you can see from this point, we have this carbon kind of pointing out towards us, whereas this one is actually pointing backwards. And then with the bottom piece of these molecules, you can see we've got these off to the sides, kind of going back as well. And these ones, this double bond is now coming out towards us. So we've got a slightly different spatial arrangement. And with this, it also, like I said, has big impacts on human health, because a lot of the times with these types of isomers, and if you take organic chemistry, you'll go into exactly what R and S represents. We essentially assign priority to the different things that are bonded to it, and then depending on if that priority increases clockwise or counterclockwise is how we get R or S. If you take organic chemistry, like I said, that'll be something that you really focus on. But in terms of human health, in a lot of cases, the human body itself can only sort of utilize one of these isomers. So in some cases, one of the isomers may be something that the body can work with, and the other one is just ineffective. Or in the case of something like thalidomide, one of them is going to be effective, and the other one can actually have hugely negative consequences. So if you're familiar with thalidomide, if you've ever heard the Billy Joel song, "We Didn't Start the Fire," he mentions thalidomide babies. And what that's referring to is the use of this substance as a treatment for morning sickness in pregnant women. So this was a drug that was used in Europe for to help pregnant women kind of deal with that morning sickness, deal with that nauseous feeling. And the R isomer, so the one at the top here, is going to be an effective sedative. So to help the women sleep, help them overcome that discomfort. But now the S isomer is going to be what's known as a teratogen. And a teratogen is just going to be something that causes birth defects. So what wound up happening is tens of thousands of children that were born from women that were using thalidomide to treat that morning sickness were born with birth defects. So they may have stunted limbs or whatever the particular defect was. And this happened in very large amounts in Europe. The years escape me. I want to say the 50s, maybe the 60s, but somewhere around the middle of the previous century. But the reason this wasn't an issue in the United States is because of Dr. Frances Kelsey. So she worked for the Food and Drug Administration. And essentially, if you want to be able to sell some medicine, some drug in the country, you need to get it approved. So you need to do trials. You need to show that drug's safe for use. And the company that produced the thalidomide submitted their evidence, but Dr. Frances Kelsey felt it was lacking. So it felt like they needed more proof to actually show that it was safe. And of course, there was pressure from the drug company on her, but there's also pressure from other people within the FDA, other people within the country itself, and especially working as a woman in science at the time, that pressure could be monumental. But she kind of just put her foot down and refused to approve the registration of thalidomide within the United States. I believe there was a small trial where they were kind of testing it, but it was never approved for just the general use. So the effects of thalidomide were never really seen in the United States like it was in Europe. And ultimately, so this is Dr. Frances Kelsey on the left. You can see JFK on the right. That's why I assume this was the 50s, but he was also president in the 60s. So depending on how much time passed between this thalidomide and her actually being awarded the President's Award for Distinguished Federal Civilian Service, I don't know exactly. So it's just going to be somewhere in the 50s or 60s range. But with it, that'll be the last piece of this little section, and then the rest of the chapter we're going to be focused a little bit on the periodic table so that we can understand how different compounds are going to form, even molecules as well. So if we think about those elemental ones, and then the difference between some of those compounds, depending on if it's ionic, that'll have a set of properties, covalent, and then depending on those types of compounds, they'll have a particular type of element involved in each.